Hello everybody, and welcome back to CIV E 398 Assignment Guide. So in this assignment guide, we're going to be covering Assignment 4, Question 3, which deals with both the small strain matrix and the green strain matrix. So once you guys figure this one out, figure out this question, you guys are good to go for strain. You guys will be experts at the small strain, you guys will be experts at the green strain, and that's all you really need to know in terms of these matrices or tensors, whatever you want to call them. So question itself says, consider the plate in the figure below. And you guys are given a plate. I'm not showing you guys the plate, but it's just a simple plate. And the reason why we give you a plate is because you guys will see we need a coordinate point to figure out parts of the question later on. And it says the displacement function of the plate is described by U1 and U2. So the nice thing is this is in 2 dimensions. We only have U1 and U2. We don't have a U3. The shitty thing is that U1 and U2 look disgusting. We got x1, x2 squared, stuff like that. It's a real mess. And the question says determine the position functions x1 and x2. So we have u1 and u2. Can we determine x1 and x2? Of course. And you guys are saying, wait a second. This question looks pretty easy. Why do you say it's not easy? Why do you say it's bad? Well, there's this part too. So the question also wants us to find the infinitesimal or the small strain component E small 1 1, the green strain component E green 1 1, the small strain matrix at the centroid of the plate, the green strain matrix at the centroid of the plate. It wants us to draw the vector plot of the displacement function and the contour plot of E small 1 1, E green 1 1, E small 1 2, and E green 1 2. So this looks gross. This looks like it's asking for so many things. You guys are going to say, oh, God, I'm going to be here forever. This is not good, Clayton. This is not good at all. But if we actually look at this more closely, all these questions deal with both the small and the green strain matrix. So all we have to do is figure out E small and E green, and that answers questions 1 through D. Nice and easy. And if we look at the second part, well, these are just plotting E small and E green. So if we actually look at this question and what we need to solve all these questions, we just need E small and E green. That's it. That's all. So the question becomes, okay, well, how do we find E small and E green? But before we do that, we're going to talk about position functions, because recall that there actually was a question that said, okay, we gave you the 2 displacement functions. What are the position functions? So remember that there's a nice easy relationship where a position function, x, can be found by taking big X and adding it to our displacement functions, u. And saying, okay, well, it looks really simple, but what exactly does this mean? Well, let's write it out in a vector form. So x1, x2 is equal to big X1, big X2, plus u1, u2. And you're saying, wait a second. If we add them together, we got u1 plus x1, big X1, and u2 plus big X2. So in order to go from a displacement function to a position function, all we have to do is add an x1 to u1 and add an x2 to u2. It's that simple. So that first part should be nice and easy. Even though the displacement functions are really gross, all we have to do is add an x1 and an x2. You guys are good to go. So now let's talk about the actual meat and potatoes of this question, which are those 2 strain tensors, E small and E green. So let's look at the formulations and figure out, okay, well, how exactly can we determine them? Well, for the small strain tensor, E small, it's equal to 1/2 of the displacement gradient plus the transpose of the displacement gradient. You guys saying, okay, well, that doesn't look too bad. It's just the displacement gradient, basically. If I know that one, I can easily find E small. Well, the second one, the green strain tensor, oh, well, maybe it's a little bit worse. Well, it's a little bit worse, but as we can see, it's 1/2 of the displacement gradient plus the transpose of the displacement gradient, also added to the transpose of the displacement gradient multiplied by the displacement gradient. So the key factor here is, wait, all we need to find these 2 matrices and answer basically the entire question is just the displacement gradient. How hard can that be? Seems easy, right? All we need is that displacement gradient. Should be good to go. Well, is it that easy? Let's find out. So the displacement gradients, we know that there's a nice simple formula to find it, and that's just taking the partial derivatives of the displacement functions, u1, u2, and u3, with respect to big X1, big X2, big X3. And you guys are saying, okay, Clayton, you scared me with this equation before, but I remember it was easy. This is actually a piece of cake. Not too scared. Well, I'm going to make it even easier for you, because remember, this displacement gradient is for 3 dimensions. Luckily for us, we're only dealing with 2 dimensions right here. So all we have is 4 terms. partial u1 with respect to big X1, partial u1 with respect to big X2, and then partial u2 with respect to big X1 and partial u2 with respect to big X2. So you guys are saying, wait a second. The key to this whole question was the displacement gradient. And the displacement gradient's only 4 terms. Something's wrong. Like, this is actually an easy question. Clayton, why do you keep saying it's hard? So we already know the displacement gradients. We can easily find those displacement gradients, the partial derivatives, right? Like, right? What's the problem here? Well, let's actually look into it. So now we know how the displacement gradient is formed. Let's revisit the formulations for the small strain tensor. So remember that E small is 1/2 displacement gradient plus the transpose of the displacement gradient. So what I can do is I can actually write it out and say, okay, well, E small is 1/2 times the displacement gradient plus transpose the displacement gradient, and I can combine it all together into one simple formula. You guys are looking at it saying, well, okay, well, if I know those 4 components of the displacement gradients, all the partial u1s and u2s, well, I can easily find out E small. That's the answer right there. So Clayton, what's so hard about this? Well, u1 and u2 are pretty ugly. So taking those partial derivatives, it's pretty gross. But if we look at this one, we can find E small. It's going to be very tedious, but it's doable. So here's where we're kind of getting on that line where it's easy to do. The formulations are easy, but it's going to be kind of messy, kind of tedious. By this point, we're probably saying, okay, well, Mathematica is looking pretty sexy right now. Well, let's go on to the green strain matrix. And this is where I will force your hand to say, yes, we're using Mathematica. So if we look at the formulation for the green strain tensor, it's very similar to the small strain tensor. We're just tacking on that little term at the end, the displacement gradient transpose multiplied by the displacement gradient. So if we write this one out, we're given this equation right here. And we're saying, okay, well, the first part, the displacement gradient plus the transpose of the displacement gradient, well, that's easy. And as you guys will see, this small strain matrix was easy because all we're doing is adding matrices. The problem with the green strain matrix is we're multiplying 2 matrices. That term right there at the end, this becomes a megabitch. You never want to deal with a megabitch. So this right here, this is where things get kind of shitty. My only advice, if you want to try it by hand, good luck. So by this point, this is my slide to say, okay, guys, we're going to use Mathematica. It's looking pretty good right now because remember, U1 and U2 are ugly. So the partial U1s and U2s are going to be ugly. And then multiplying 2 matrices full of those ugly things, don't even try it. It's getting really ugly. Let's use Mathematica. Because as you guys will see, Mathematica makes it very nice. So all we need to do is define the displacement functions and variables we need to differentiate. So what I did is I made a vector U1 and U2, and I previously defined U1 and U2. So U1, of course, will be X1, X2, blah, 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 and same with U2. And then I create a second vector, big X, which is big X1 and big X2. So all we need to do to find that displacement gradient, because remember the key here is the displacement gradient, is using the table function. So what this is it's kind of like a for loop, kind of iffy. You guys don't really know what it's like because all you guys are going to have to do is type in this formula where we say the gradient to u is table. And what I did is I took the differential of ui with respect to xj. And then what I did is I defined I as 1 and 2 and j as 1 and 2. So for instance, this is going to kind of loop through and go, okay, well, it's going to take the partial of u1 with respect to x1, and then the partial u1 with respect to x2, and then the partial u2 with respect to x1, and so on and so on. So all you guys are going to have to do in Mathematica is type this formula out, and as long as you guys have defined u1 and u2 correctly, this will give you the gradient of u. And if we have the gradient of u, well, we say everything else is easy. Because if we look at the formulations for our small strain tensors, E small is equal to 1/2 gradient of u plus the, displacement gradient plus the displacement gradient transpose. Well, I can easily throw that in Mathematica as E small is equal to 0.5 multiplied by gradient of u plus the transpose of gradient of u. Nice and simple. Again, that hard part was just defining that gradient of u in Mathematica. This green strain tensor gets a little bit tricky only for one reason. It's equal to 1/2 of the displacement gradient plus the gradient transpose of the displacement gradient plus the transpose of the displacement gradient multiplied by the displacement gradient. Oh my god, that is a mouthful right there. But as you guys can see, It's easier just to look at the picture. You're saying, okay, well, in Mathematica, all we have to do is this. 0.5 times grad u plus the transpose of grad u plus the transpose of grad u times the grad u. Now, the only key that I'm going to have to say, please remember, is this term right here. When we're doing matrix multiplication, we use a period. We're not using a star. If you guys use a star where that period is, you guys will get the wrong answer. So the only real trick here is to remember we need a period there, not a star. But after that, nice and easy, everything's looking pretty good. We'll have our green strain matrix and we'll have our small strain matrix. Well, at least it would be easy until we say, okay, Mathematica, now I want the components. How on earth do I find the components? So there's two things we can do. We can define them as variables. So in terms of x1 and x2. So what I can do is I can, if I wanted to call, let's say the green strain matrix entry 1, 1, all I have to do is go E green, double square brackets, 1, 1. Here's the key here. We want those double square brackets. If you do a single square bracket, it's going to think you're calling a function, which is why we have the double square brackets, because we're not calling a function. We're just calling the terms inside of the green strain matrix. So if I were to go E green, double square brackets 1, 1, it'll call my green strain matrix entry 1, 1 in terms of x1 and x2. For instance, it'll say the entry is x1 squared plus x2 cubed, whatever. And which is great because some of the questions want it exactly that in terms of x1 and x2. But we can also call it just as a single number. So we can sub in values of x1 and x2. So the formulation is the exact same where I go E green 1, 1, and then I do a backslash dot. And what this means is basically, in Mathematica words, win. So I say I want my green strain component 1, 1, win, and then I go x1 is 2, and x2 is 4. So all you're going to have to do is say x1, and then you do a little arrow, and you can define what it is. In this case, I want x1 is equal to 2, and I want x2 is equal to 4. So this calls the component 1, 1 of the green strain matrix when x1 is equal to 2 and x2 is equal to 4. So this basically answers all the questions from before. As you guys will see, nice and easy. The only difference you guys will have to remember is this. You can add, you can substitute values by adding this little little piece of code to the end of your green strain matrix or your small strain matrix. Alrighty, so moving on, last part of the question, vector and contour plots. Well, as you guys will see, now that we already have our green strain matrix and our small strain matrix, vector and contour plots are actually a piece of cake. So for a vector plot, we use a function vector plot. So inside of there, we're going to have three different arguments. We're going to have the function, and then we're basically going to define where we want to span that function. So we have x and we have y. You're saying, okay, Clayton, doesn't sound too bad. What is function? Well, we'll discuss that in a bit. If we want a contour plot, it's the exact same, but the only difference is instead of vector plot, we're putting contour plot. So as you guys will see, these are the exact same. The only difference is vector, contour. That's it. That's simple. And you're saying, okay, Clayton, well, it is simple, but what exactly is function? What exactly is x min, x max, stuff like that? Well, our function will be what we want to plot. So in this case, if we want the small strain matrix entry 1, 1, all we're going to type here is E small, double square brackets 1, 1. So that'll be my function. And I say, okay, well, I want this from x1 between 0 and 2. So I define the variable on the x-axis. In this case, I want x1, and I say it's going to range from 0 to 2. And then finally, I'm going to define the variable on the y-axis. So in this case, I put x2, and I want this between 0 and 2. So nice and simple, and these will also apply down to the contour plots. So this question looks really bad, but once you guys realize, hey, I should not do this by hand, I should definitely be using Mathematica, the question becomes pretty simple. So I hope this tutorial helped you guys a little bit. This is definitely the hardest question of the assignment. Questions 4 and 5, nice simple 2-slide questions. So at this point, you guys should be cheering. Yay, the hard part's over. And you guys can kind of relax now. The rest gets nice and simple. So thank you guys so much for listening. I really appreciate it. I will see you guys in question number 4.